Hello everyone, my name is Rafael Gitti. I am PhD researcher at Federal University of Santa Catarina. Today we present a work entitled Changes to Fabricate Functionally Graded Rare Earth-Based Permanent Bonded Magnets via Powder-Based Additive Manufacturing. This presentation is divided as follows: a brief introduction about functionally graded materials, additive manufacturing process of this class of material, and the challenges about the AM of functionally graded magnets. Then we will move to the objectives of this work, adopted experimental procedure, achieved results, and the outlooks and future perspectives of this topic. The functionally graded materials are a class of materials with variable properties in one or more directions in space, induced by gradual changes in the composition, chemistry, or microstructure. These graded structures can be presented throughout the material or located in specific regions, resulting in components with heterogeneous properties. Conventionally, these materials are obtained via gas, liquid, or solid phase reactions in the form of bulks, thin films, or coatings, producing gradients in the millimetric range. With additive manufacturing technologies, it is possible to obtain components with non-usual geometries allied to the gradual variation of its properties. The layer-by-layer construction principle enables a variation of properties in the micrometric range in the order of the layers, giving rise to the new functionalities. Also, with the additive manufacturing processes, it is possible to work with a wide range of materials. One of the most promising candidates for gradient functionalization are rare earth-based permanent magnets, gathering both functional gradient and geometrical complexity features. Several properties can be varied within the same magnet, such as corrosion and demagnetization resistance. One of the most promising features is the manipulation of the stray field in the space for sensing devices. The stray field manipulation can be produced by many approaches. A variation in the composition of the magnet in a preferred direction or location can produce this effect. Also, controlling the porosity or distributing them in certain regions can produce the same effect. The first approach was reported by Hilbert and co-authors, where bonded magnets were obtained via extrusion-based additive manufacturing, varying the fraction of magnetic compound in a direction. This approach resulted in a stray field distributed as shown in the image. Another approach is to control the porosity level in the S-printed magnetic samples. This was reported by Finn and co-authors, which presented the influence of processing parameters and feedstock composition in porosity level of neodymium atom-boron bonded magnets, obtained via powder-based AM. In their work, bonded magnets were obtained varying the fraction of binder in the feedstock and the processing parameters, such as laser scan speed. By the combination of laser scan speed and binder fraction, it was possible to obtain S-printed magnetic samples with porosity varying between 31 and 5%. Since magnetic properties are proportional to the porosity degree of the magnet, this emerges as potential candidate to obtain functional graded bonded magnets. Inspired by this context, this work aims to investigate the obtention of functionally graded neodymium and bottom bonded magnets, obtained via powder-based additive manufacturing. The main objective is to obtain magnetic samples with variable porosity in a specific direction via laser scan speed variations, without changing the feedstock composition. In this way, magnetic samples were obtained via selective laser sintering processing, following parameters described by Finn and co-authors as listed in the table. The laser scan speed was the only variable processing parameter, ranging from 600 to 1600 millimeters per second. A feedstock composed of 45% in volume of polyamide and 55% in volume of neodymium atom-boron isotropic powder was used. In this investigation, cubic samples with dimensions of 20 by 20 by 20 millimeters each were obtained via selective laser sintering following two different approaches. In the first one, the called sample A design consisted to printing samples varying the laser scan speed in the building direction. At every 5 millimeter section, the laser scan speed value was varied, starting in 600 millimeters per second up to 1600 millimeters per second, promoting a gradual variation in the laser scan speed values. The second one, the called B sample design, consisted to print alternate 5 millimeter height sections, using only the extreme laser scan values. For comparison purposes, reference samples were obtained employing each laser scan speed value, varying the height between 20 and 5 millimeters, called respectively samples C and D. The obtained samples were characterized via geometrical density measurements, scanning electron microscopy, and magnetic flux density measurements. From geometrical density measurements, both in A, B, and C samples presented the same geometrical density values, indicating that both approaches induced similar porosity levels. In the comparison to the reference samples, the results are also similar. This indicates that either A, B, and C samples were submitted to similar thermal conditions, leading to similar porosity levels. Comparing the C and D samples, it can be seen that samples with the 5 millimeters height were systematically more porous than those with 20 millimeters for all laser scan speed values explored. The results present that regardless the strategy adopted, all conditions resulted in similar porosity levels, possibly due to thermal effects of the own nature of the LPBF process. The heat diffusion from the denser layers throughout the porous ones can lead to this condition, where porosity is eliminated instead of retained. The thermal energy stored during the laser powder bed diffusion process assists the sintering processes of polymeric particles. This is evidenced by the reference samples with different heights. 20 mm height samples were exposed to more heating cycles than the 5 mm height samples, leading to different porosity levels of the same processing conditions. From SAM observations from the fracture surface of the S-printed magnetic samples, it is possible to observe that the variations in the laser scan speed promoted alterations in porosity level. In the A image from a region built with 600 millimeters per second of laser scan, which is a higher energy density, it can be seen that great part of the section is composed of polyamide encapsulating the magnetic particles with located pores. As the laser scan values increases up to 1600 millimeters per second, the energy density is reduced and therefore a more porous region is formed. In the B image from the same sample, this region now is majorly composed of pores. A similar microstructure is observed in the A sample. The figure A is from the region built with elevated energy density and B with the reduced energy density. SAM observations present that both approaches were effective to induce different porosity levels at some extent. The magnetic flux density measurements at the surface of both A and B samples revealed that magnetic flux density is homogeneous. As presented earlier, the geometrical density values are similar for both samples, leading to similar magnetic properties. Despite the SAM observations revealed this different porosity level, this was not sufficient to promote the variations in the stray field. The outlook of this present work is neodymium bonded magnets were successfully produced by laser powder bed diffusion, employing the adopted experimental procedure. Variations of laser scan speed values promoted the porosity control at some extent, as revealed by SAM. Magnetic measurements revealed that stray field was homogeneous along the scanned area. The thermal effects of the laser powder bed diffusion process leads to densification instead of retaining porosity level. As future perspectives, different strategies must be developed in order to control porosity level in a perfect direction for these purposes, such as influence of other laser powder bed diffusion parameters. Currently, our group is investigating the other laser powder bed diffusion parameters and their influence in porosity control for functionally graded bonded magnet subintention. Thank you.